Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good afternoon. Thank you for coming. I'm glad to have Martin Esther. He's an associate professor in Department of Computing Sciences at Simon Fraser University in Vancouver. He's also the director of databases and data mining group. And today he's going to talk about his work on joint cluster analysis using both attributes and relational data. And this, if I remember right, this is work from the SIAM Data Mining Conference last year, where it was one of the best papers presented. So we're glad to have him here this afternoon.
Thank you very much, Aaron. Welcome to my talk, everybody. Thank you for the invitation. I appreciate the opportunity of introducing you to some of our current research and trying to explore some common interests. The talk is about joint cluster analysis of attribute data and relationship data, problems, algorithms, and applications. I'm trying to present a mix of some theoretical and some more practical results. So if you are more theoretically minded, please hang out. If you are more practical minded, please hang out. You will hopefully both find some good nuggets in this talk. Please feel free to interrupt me whenever you want to, whenever you have any questions or comments throughout the talk. I want to keep this as interactive as possible. So cluster analysis is one of the primary data mining tasks that has received a lot of attention in various communities for decades already. The purpose of clustering is to find groups, the so-called clusters of objects with internal cohesion and external separation. It means we want to group objects together into clusters that are as similar as possible to each other and as dissimilar as possible from objects or entities of other clusters. The slides presents two toy two-dimensional data sets with more or less significant cluster structure. It immediately tells us that there are more obvious and less obvious, more difficult cluster structures hidden in data sets. If you look at the data mining and machine learning literature, the majority of clustering algorithms would be attribute-based. Normally, they use the attribute values to determine a certain pairwise distance function, which is then the main ingredient of a clustering algorithm. Partitioning clustering algorithms such as k-means, hierarchical clustering algorithms such as single link, density-based clustering algorithms such as DB-scans would all be representatives of this category of clustering algorithms. Another major class of clustering algorithms is graph-based clustering algorithms, which assume a graph-based data representation and would then lead to some kind of minimum cut graph partitioning problem in order to partition the graph into subcomponents which would correspond to hopefully meaningful clusters. Now it's worth to point out that there are very few clustering algorithms that consider both types of data. Attribute-based clustering algorithms would normally focus exclusively on the attribute side of things, whereas graph-based clustering algorithms are normally focusing more or less exclusively on the discrete relationship data. However, in many practical applications, objects do have both aspects, attributes and relationships. Attribute data describing the intrinsic or internal characteristics of objects, relationship data describing the extrinsic, external influences and relationships among objects. Market segmentation will be one of our running examples. It can be considered as an example of a broader class of community identification problems, where we would have objects, namely customers, described by demographics, age, gender, income, and so forth, classical attribute data, as well as social relations, which naturally would be represented as relationship or graph data. But many other applications have similar properties. If you look at documents would be represented by both term frequencies and co-order relationships. Genes can be represented by the gene expression profiles, measuring the degree of expression of genes in certain conditions or experiments, as well as the relationship between the corresponding proteins, as represented by some protein-protein interaction network. Crimes, we mentioned this already earlier, crimes can be represented by crime frequencies, as well as certain relationships among crime locations as represented by some underlying road network. Images, quite different application. In images, the objects would be pixels that could be described by certain color values, as well as the neighborhood relationship, the spatial neighborhood relationship among pixels. Now, why should we consider both attribute data and relationship data in clustering? Obviously, if attribute data and relationship data are more or less redundant, and in the extreme case can even be derived from each other, then there would be no point of using both data simultaneously. And of course, there are such applications. We are not trying to argue that in every case this is meaningful. There are certainly these cases where attribute data and relationship data are relatively redundant. However, there are also many cases, as we argue, where attribute data and relationship data are complementary and do indeed provide additional information compared to using only a single data type. Now, at the abstract level, the purpose of using both data types is to help resolve ambiguities in the clustering obtained when using only one of the data types. Now let me use this abstract example here to illustrate this point further. Let's assume we have these 8 objects described by the attribute, 2-dimensional attribute values only. Now when trying to find k equal to 2 clusters, the red object in the middle seems to be critical. The assignment to one of the 2 clusters is ambiguous. Now, when taking into account the graph or relationship data and learning this kind of relationships among these objects, it immediately becomes clear that this critical object should be assigned to the left cluster because it's much more closely connected to this cluster than to the right cluster. There are also situations where the opposite holds, assuming that we have a small data set represented by the relationship data only. Now the assignment of this critical object here in the middle would again be less than obvious. Now by adding the attribute data as a second layer, a second perspective, we can easily resolve this ambiguity and assign this red object to the right cluster because it's significantly closer in terms of attribute values to this cluster. Now coming back to our concrete application of market segmentation. In market segmentation, we have customers with demographics data, as we have seen already. Customers with close demographics are much more likely to respond similar to a certain product offer or campaign. So attribute data is certainly important for market segmentation. However, people are skeptical and trust their friends more than any companies or anonymous offers. So it has been increasingly recognized in the literature and I guess in industry as well that relationship data, social networks need to be taken into account for market segmentation or for marketing as well. So market segmentation seems to be driving application which motivates joint cluster analysis of attribute and relationship data. Now let me briefly outline the rest of this talk. I will briefly discuss some related work, and please feel free in particular to interrupt me there and ask a question. Obviously I need to be kind of selective in the choice and discussion of related work. I would be glad to discuss any further related work that you may want to discuss. Afterwards, I will introduce our formal problem definition in this framework of joint cluster analysis, introducing the connected K-center problem, as we call it. We will discuss algorithms. We'll start with approximation algorithms and then move on to more practical heuristic algorithms. We'll discuss applications, including some more or less preliminary experimental evaluation on real-life data before concluding this talk. And as Aaron mentioned, this talk is based on our SDM SIM data mining conference paper last spring, as well as on some follow-up work that we have recently submitted to journal. Multi-relational clustering is probably the first area that comes to your mind when thinking of joint cluster analysis and related work. In general, in multi-relational data mining, we deal with multiple tables rather than individual single tables as used in propositional classical data mining methods. Now, when clustering one of the tables in multi-relational clustering, we would consider not only the single table and its attributes, but also relationships to other tables as well as attributes of these related tables. Now, there has been some work on multi-relational clustering. In my opinion, the probabilistic relational models-based approach is certainly seminal work in this area on multi-relational clustering. There are others as well. This was work by Tasca et al. Back in 2001. Probabilistic relational models were introduced as a first-order generalization of the well-known Bayesian networks. They consist of two components different from Bayesian networks that consist of a single graph structured network only. They consist of the relational skeleton, as they call it, which corresponds to the database schema, as well as the relationships between variables representing attributes of the participating tables. And secondly, the so-called unrolled network, which corresponds closely to the database instance, to the set of tuples from different tables. Now, when using a PRM for clustering, we would have to add unobserved variables, one variable for each of the participating tables, representing the unobserved, unknown, a priori unknown cluster membership. Now, this slide presents a simple example of a probabilistic relational model from a medical domain. So we have three tables here, one table for patients, another one for strains of infectious bacteria or viruses, as well as the third table for contact persons. The arrows represent direct dependencies between variables of the same or different tables. The dotted areas represent the foreign key relationships between tables that are expressed and are known from the relational database schema. So, and this is actually, this PRM here is not using any unobserved variables. So this is the basic PRM that is normally used for classification rather than clustering purposes. Just to briefly dive into one of these variables here to clarify the meaning a little bit. This variable transmitted, for example, according to this network here, depends directly on the close contact variable or attribute of the same table, the contact person of reference. It also depends directly on the HIV result of patients, of all patients that have interacted with this particular contact person. Yeah, and then basically for each node we would have a conditional probability table very similar in style to the Bayesian networks. The other area that I briefly want to mention as related work is semi-supervised clustering. Based on the observation that cluster labels are sometimes known in advance for some of the objects, obviously not for all of the objects, but for some of the objects. This observation motivated the introduction of constraints on pairs of objects. Must-link constraints that express a constraint that two linked objects must belong to the same cluster. Cannot link constraints express a situation that the two linked objects should not belong to the same cluster. Now it turns out that these constraints are not necessarily simultaneously satisfiable in a certain context, which implies that normally these constraints are considered as soft rather than hard constraints. Now this leads us to the problem of semi-supervised clustering, which aims at discovering a good clustering with respect to attribute values in the classical non-supervised setting, that on top of this classical objective function respects the given must-link and cannot-link constraints as good as possible. Now again, this topic has received a lot of attention. I'm selecting just one of the best papers, in my opinion, here to briefly introduce some more concepts. Basu et al. Have proposed the probabilistic framework back in 2004, which is based on hidden Markov random fields, where the observed variables represent attribute values or data points. The hidden variables represent, again, the cluster labels, edges or neighborhoods represent both must and cannot links. Now, so we have the observed data here on the upper level, the hidden class labels, as well as the links on the lower level. In this case, we want to find k equal to 3 clusters. So based on the must links, we know that x4, x1, and x3 must belong to the same cluster, say cluster 1. We know that x6 cannot be linked with either of these objects, so this would fall into separate the second cluster. Now x5 and x2 are not participating in any constraints, so we have all the freedom to assign them to either of these three clusters that we want to find. Now remember that we also want to minimize the clustering cost. We want to maximize the compactness of the corresponding clusters. So consequently, x2 would be assigned to this first cluster because it's close to its centroid, whereas x5 would be too far away from the centroid. It would be more effective from the point of view of maximizing the objective function to include it into a new cluster, the third cluster. So we have already mentioned constraints in clustering. Now these pairwise must-link and cannot-link constraints are a very specific kind of clustering constraints. There's more general cluster constraints available in many applications, and this has led to another field called constraint clustering, both in data mining and machine learning. Researchers have developed different formalisms and corresponding algorithms to express constraints such as cluster cardinality constraints, constraints on the average values of clusters, and so forth. So basically different from the semi-supervised clustering, these are all cluster level constraints. The semi-supervised constraints are all instance level constraints, relating pairs of instances. Now, these constraints are typically cluster or class level constraints constraining a certain set of objects grouped together in a cluster. Now, many of these constraints can be formulated in SQL. This has been used as one of the languages to express such constraints. Tung et al. Have suggested one of the first constraint clustering algorithms in 2000, constraint partitioning clustering algorithm. Let's briefly illustrate this for this case of two-dimensional points. Assuming we want to find k equal to 2 clusters, and we restrict the cardinality to be at least 4. Now, obviously, the 3 guys on the right side would violate this cluster cardinality constraint, so we would have to include the closest among the objects on the left-hand side from the natural cluster on the left-hand side to form a first cluster satisfying the cardinality constraint. The remaining objects would be included in the second cluster in order to maximize the value of the objective function, or minimize the average distance between a point and the corresponding cluster center. Yeah, are there any questions concerning related work or any comments? Okay, then I'll move on. Let's come on to our problem definition for joint cluster analysis. So the first question that we need to address here is, if we want to combine attribute and relationship data, how do we want to combine these two data types into a single coherent problem definition? And as we have seen in our discussion of related work, there are essentially 2 alternatives. We can either perform multi-objective optimization, simultaneously optimizing an objective function on both of these data types, or alternatively, we can formulate the problem in a somewhat asymmetric manner, using one of the data types for constraining the solutions, using the other data type for defining some objective function that would be optimized. And we have investigated the second approach. Now, considering the characteristics of the 2 data types, namely that attribute data is inherently continuous or normally continuous, not always, relationship data is discrete, we are using the relationship data to define constraints and using the attribute data to define objective function that would be optimized. Now, similar to semi-supervised clustering and to constraint clustering, and different from multi-relational clustering, we are dealing with the case of a single table only. So this is not multi-relational data mining. Now, given a data set, capital D, as a so-called informative graph, a graph where nodes are associated with attributes or attribute vectors, with a node set, capital V, and an edge set, capital E, K, the number of intended clusters to be discovered, connectivity constraint, that clusters need to be connected graph components. This is the connectivity constraint that we formulate on the relationship data. The classical objective function that we know from many partitioning clustering algorithms, namely that actually, sorry, I need to be careful. This is not the objective function that we are using in the connected K-center problem is measures the maximum distance between cluster nodes and cluster center. So basically, we take the radius of clusters as the objective function. You may wonder why we are using this. We are using this because this makes it possible to analyze the complexity and makes it possible to develop approximation algorithms. As we'll see later, the resulting practical heuristic algorithm can easily be applied to the corresponding k-means version of our problem, where we use the average distance between a point and the corresponding cluster center as the objective function. So taking these ingredients, the task of the connected K-center problem is as follows. Find the K-centers, K-nodes from our informative graph, and the corresponding partitioning of D into K clusters, such that first each cluster is internally connected, meaning every pair of nodes in the cluster is connected via a path of objects from within this cluster. Secondly, the objective function is maximized. Minimized, of course. The radius is minimized.
So you say so the center has to be one of the nodes?
Yes.
Or are you introducing some dummy variables that represent the center? That's what I don't get that clearly. So that either the centers have to be one of the nodes.
They have to. The centers have to be. The centers have to be nodes, objects of our database.
So the idea is, given a hypothesized cluster, you find the node that minimizes radius.
Yes. So we find K centers, K nodes, and the unique assignment of the remaining nodes to one of these K centers, such that each of the K clusters is internally connected and minimizes the overall cluster radius.
So can you talk a little bit more about the logic behind making the nodes themselves centers? Is that a little bit restrictive?
Rather than using virtual points like means?
Yes. Because I can think of strange scenarios where having the nodes themselves as centers may not work at all.
Yeah. Let me say, if we forget the joint cluster analysis for a second, if we go back to classical partitioning clustering algorithms, we have two main paradigms here. We have the k-means-like clustering algorithms and the k-medoid-like clustering algorithms, right? So even in classical partitioning clustering algorithms, we also have this. This is a well-accepted paradigm of representing clusters either by a cluster element or by a cluster, by a virtual point, the gravity center of the cluster, right? Obviously, let me say, you have the k-means problem is in a way easier than the k-medoid problem. On the other hand, the k-medoid problem is more general because it doesn't require points to be represented in a Euclidean vector space, right? So it's more applicable because it just requires a pairwise distance function. So it's, this certainly, it certainly has, and let me see, maybe we move on to the next slide where we motivate this problem once more in our running example of market segmentation, right? It's, so, to illustrate the meaningfulness of the problem definition. And certainly it's, there are some limitations when you require cluster centers to be data objects. However, we feel that in many applications this is acceptable. Now take a market segmentation again. Now our cluster model, this connected K-center problem, corresponds to an approach where we design a specific product offer or campaign or product bundle for a certain customer group, for a certain market segment. You send the offer to the cluster representatives, to the representatives of each of the K clusters. So in this case, you would certainly want to send it to a real person. And then let the customers propagate the offer within their segment if they like it. Now the center nodes serve as cluster representatives. The connectivity constraint in this case allows us to model the word-of-mouth phenomenon. The objective function seems to make sense because the smaller the radius, the smaller the distance between cluster elements and their corresponding representative, the more similar their demographic data, the product, the purchase preferences, the more likely that cluster elements will like the offer and propagate it further.
So the path length from a central node to the the average path length or the maximum path length also within a cluster would also talk about how easily things will propagate.
Yes.
Do you look at that at all?
You mean the average path length?
Yeah. The average or maximum, whichever.
Yeah, let me see. Let me see. In this is the theoretical problem definition. In this problem definition, we just consider the radius. We'll briefly mention this later. We can easily replace the objective function by an objective function that minimizes the average distance between cluster elements and the corresponding center. Obviously, we can come up with stricter connectivity constraints. And we'll talk about this a little bit later, actually quite at the end of the talk in our future work. So this was the first step into this direction of joint cluster analysis. So we had a relatively theoretical approach. But as we'll see, we also have some practical algorithms and we have some experimental results. Now, but let's discuss the theoretical aspects. First, how hard is the problem? Does it make sense to find correct, complete, exact solutions to this problem? And it turns out that the connected K-center problem is very hard. It is NP-complete for K equal to 2 clusters, even for the simplest case of D equal to 1 dimensions. So it's even harder than the classical K-center problem and related problems. The proof uses a reduction from the 3CNF SAT problem, and I just briefly want to sketch the idea of this proof. The 3CNF SAT problem is defined as follows. Given a set of variables, capital U, with n variables u1 to un, a Boolean formula C, which is a conjunction of m subformulas C1 to Cm, where each of these Ci is the disjunction of exactly 3 literals, and each of the literals is either a variable or a negated variable from our alphabet capital U. Decide whether there exists a truth assignment of capital U that makes C hold in order to prove the NP-completeness, in order to reduce the CKC problem from the SAT problem. We need to consider a decision version of the connected K-center problem, where instead of optimizing the radius, we ask whether for a certain radius R, there are K-centers such that all nodes can be assigned in a connected manner within radius R to one of the K cluster centers. So this is the decision version, the equivalent version of the connected K-center problem. Now let's briefly illustrate the idea of the reduction. We assume K equal to 2 and D equal to 1. The simplest case, the proof can easily be generalized to other cases. Now, obviously, the task here is to model the 3CNF SAT problem as a connected K-center clustering problem. Now, how do we do this? We introduce nodes for the subformula C1 to Cm, one node each. We introduce nodes for the variables and the negated variables u1 to un. We introduce 2 nodes that will be serving as cluster centers. We want to find K equal to 2 clusters. Now we have these technical gadgets here at the top, A1 to AN and B1 to BN, which will make sure that UI and UI bar must be in different clusters. Right? This is a constraint that is inherent in the logical SAT problem. Right? A variable is either the variable or its negation is true. Now let's look at the attribute side of things. We basically order the nodes on this one-dimensional axis here. So, and this axis represents the single attribute values. So all b's obtain a value of 0. P0 gets a value of r, the given radius r. The variables ui and not ui get a value of 2r. P1 ends up with a value of 3r. And the remaining nodes, ai and ci, get a value of 4r. Now, if you want to find two clusters satisfying this radius constraint, we have no choice than to use P0 and P1 as the two cluster centers, to assign the BIs all to P0, the AIs and CIs to P1, and for the UIs and not UIs, we have the choice to assign them to either of the two cluster centers, right? And using these technical gadgets here and the corresponding edges in our chosen graph, we can make sure that each of the UIs must be in different clusters. Now, the interpretation of these clusters is as follows. The cluster of P0 will serve as our faults cluster. So this will contain all variables that evaluate to faults, whereas the cluster P1, centered at P1, corresponds to the true cluster containing all variables UI that evaluate to true in our formula. Now, in order to make the basically CI, as we said, must be part of the P1 cluster. So consequently, every CI must be connected to P1 via at least one of its literals. Right? So every CI is related to I forgot to mention this. Every CI is related to the three literals that occur in the subformula. Now, in order to enforce this constraint, every CI must be connected to P1 by at least one of its literals, which is exactly equivalent to the formulation of the 3C or requirement of the 3CNF SAT problem, namely that in order to evaluate the entire formula to true, each of the subformulas must have at least one valid literal. So this is the idea behind the reduction of the connected case center problem from the 3CNF SAT problem. Now, this was the abstract proof. There's also some way of intuitively illustrating the hardness of the problem. Given case centers and the radius r, even in this situation, when we have already certain k centers and a given radius, finding the optimal assignment for the remaining nodes is already NP hard. This can be seen easily from the following example. The reason is that there are some critical nodes that we call articulation nodes that are within radius r from more than one cluster center, and from which other nodes depend in their assignment. So, for example, in this case here, the assignment of node B depends on the assignment of articulation node A. As soon as we assign A to cluster 1, B needs to be assigned to the same cluster. If we assign A to the second cluster, B would have been assigned to the second cluster as well. So the assignment of different nodes is not independent, which is different from the classical k-means or k-center problem, where as soon as we have found k-centers, the assignment of the remaining points is straightforward because it's independent from each other. So this is intuitively the reason why the connected k-center problem is so hard. Now, given that the problem is NP-complete, there's no hope of coming up with an efficient algorithm that finds an exact solution to the problem. However, as we'll see, it is possible to construct an approximation algorithm that finds a solution with a certain quality guarantee, a solution that is not more than 3 times as expensive as the optimal solution. This algorithm works in a polynomial runtime. It makes use of a relaxed version of the CKC problem that we call CKC prime problem. It's very similar to the CKC problem, except that it allows clusters to overlap. This is the relaxation. Now we will show how to solve the CKC prime problem in polynomial runtime. We consider every possible radius R, and the possible radii are those pairwise distances of nodes. We consider them in increasing order. Now for a given R, we try every combination of k centers, k of the n elements of our data set, or k of the n nodes of our informative graph. We perform a breadth-first search up to a radius of R, starting from each of the k currently considered cluster centers. Now this breadth-first search, this limited breadth-first search, allows us to determine whether the problem, the CKC prime problem, is solvable for the given k cluster centers and the chosen R. Right? As soon as we find the solution, we terminate. So this algorithm finds us the exact solution to the CKC prime problem in polynomial runtime, in runtime of the order of n to the power of k plus 2 times log n. And the main cost factor here is the enumeration of these k, or combinations of k cluster centers. Now, the second ingredient that we need for our approximation algorithm is the conversion of a solution, given exact solution to the CKC prime problem, called C1 prime to CK prime, with respect to radius R, into a solution C1 to CK of the original CKC problem with respect to 3R. So we lose, quite not surprisingly, we lose some accuracy with this conversion. This conversion keeps the same cluster center, so we don't touch the cluster centers that were found for the CKC prime problem. But obviously we need to assign nodes uniquely to one of the clusters. This is the main challenge. Now the algorithm works as follows. We iterate over the k clusters, Ci from 1 to k. We first deal with the nodes of Ci prime. When we basically build cluster Ci. We first consider the nodes of Ci prime that have not yet been assigned to another cluster. We want to keep them as far as possible in the same cluster. Again, we perform breadth-first search up to a radius of R. Now comes the difficult part. Now we need to deal with the nodes that are reachable only via some articulation node. So we deal with the nodes that were part of Ci prime in the relaxed problem, that were reachable via an from Ci, that were reachable from Ci, the center of Ci prime, via an articulation node that has now, in the unique or in the partitioning, has now been assigned to cluster Cj, j smaller than I. So this articulation node is gone already into another cluster, right? And now this node happens to be unconnected to the center of Ci in the partitioned solution of the data set. So sorry, I forgot to mention. So this is a problem. What do we do with this point? We assign this point now to, the only thing that we can do is we assign this point to the point to which its corresponding articulation node has been assigned previously already. Now the question is, how much accuracy do we lose? Now let's illustrate this situation with this slide here. Let's assume that the yellow node, Vp prime, is this articulation node shared by C1 prime and C2 prime. Now this red node, Vp, is a node that depends on the assignment of this articulation node. It was a part of C2 prime. It was within radius R from C2. It's no longer connected to C2 because we assigned Vp prime to C1, the earlier cluster C1, right? Now, how much can we lose? Let's briefly analyze this. We know that the distance between Vp prime and C1 is bounded by R because this node is part of both C1 and C1 prime. Now, the distance between Vp prime and Vp prime, this is basically the loss when assigning VP prime to C1 rather than to C2. Right? This distance is due to the triangle inequality. It cannot be larger than the sum of the distances between VP prime and VP and the distance between VP prime and C2. Now, we know that both of these distances must be bound by R. Why? Because this VP prime was part of C2 prime, and it is also right. So both of these distances are bound by R. So consequently, the distance between VP and VP prime is smaller or equal to 2R. Now, taking these two terms together and applying the triangle inequality again, we can prove that the distance between VP prime and C1, the new cluster center to which we assign it in the unique solution, cannot exceed 3R. So now taking together this exact solution, this exact algorithm for the CKC prime problem and this conversion algorithm, which is the 3 approximation algorithm, we obtain a 3 approximation algorithm for our original CKC problem. Okay, so this approximation algorithm is theoretically satisfying. It delivers this desirable performance guarantee. Its polynomial runtime, unfortunately, as we have seen, the polynomial runtime is relatively high. It's, the runtime is higher than n to the power of k already because of the expensive enumeration of all combinations of k cluster centers. Consequently, we have developed a heuristic algorithm that scales well to large databases. We call this algorithm NetScan. The overall algorithmic scheme is very similar to many optimization algorithms such as k-means. So in the first step, we initialize k cluster centers somehow. We'll see this in a second. We assign the remaining nodes to one of the k-current cluster centers. We recalculate centers, and we continue until convergence. Now, and we mentioned this already, I want to point this out here once more. The same algorithm, NetScan, can be used to solve not only the connected k-center problem, but also the connected k-means problem. Basically, we needed the connected k-center problem mainly for the sake of being able to analyze the quality and to come up with an approximation algorithm. As soon as we don't need the approximation guarantee anymore, we can easily replace the centers by the means. Okay, so the main challenge, as we've seen already, of the heuristic algorithm is the assignment of the remaining nodes to k current cluster centers. Everything else is straightforward. And in principle, we would like to grow the k clusters in parallel, assigning points or nodes to one of the k cluster centers as soon as they become connected with respect to the current radius r. Now, it is a sequential simulation. We incrementally increase the radius r, starting with a small initial radius r0, iterating for current radius ri, iterating over the k cluster centers, assigning all nodes to ci that are reachable from ci with a breadth first search within distance ri. If not all of the nodes have been assigned within the current maximum radius ri, we increase ri and resume from steps 2 until all nodes become assigned to one of the clusters. We also perform some limited look ahead to treat the articulation nodes that we have mentioned already. Now, this slide illustrates the idea of the NetScan algorithm once more. So in this case, we want to find 2 clusters, and we have 2 current cluster centers, C1 and C2. Now we start with the initial radius R0. No node is connected to C1 within this radius. One node at the bottom is connected to C2 for this radius, so there's still some unassigned nodes. We continue trying the next larger radius R1. Now within R1, U and V become connected to C1. However, now V is one of these critical articulation nodes. Assigning V to C1 would imply that W would also have to be assigned to C1, and W would not be reachable within radius R1, so consequently we need to continue. We try the same radius for C2. The same problem applies. U would be the complicated outlier in this point of view, so we need to continue. Within R1, V can neither be assigned to cluster C1 to C2, so we try the next larger radius increment R2, within which all nodes are connected and reachable from cluster center C1. And we are done for this small toy example. Let's discuss some more algorithmic challenges here. It's well known that the initialization of all these optimization algorithms is crucial. We propose a random initialization of cluster centers with a certain modification. We weight the probabilities of drawing a particular node as a cluster center with its degree, based on the intuition that higher degree cluster centers have a higher probability of generating a larger connected component. It's only a heuristic. The radius increments are another important ingredient of the method. And there's a trade-off as follows. The more increments we consider, the more accurate becomes our solution, the smaller the radius of the solution that we discover. Of course, on the other hand, we possibly unnecessarily increase the runtime of the algorithm. So we have proposed a compromise to set the radius values and in particular the radius increments. The treatment of articulation nodes is one of the main challenges of the method. And again, we are proposing compromise here. As we know from the theoretical analysis, we cannot expect to efficiently consider all solutions and find the optimal solution. So what we do is, as a compromise, we consider only the unary neighbors, the degree 1 neighbors of articulation nodes. These neighbors are, on one hand, extremely critical because there's only one way of connecting them to one of the k current cluster centers. And secondly, these unary nodes can be efficiently dealt with. So this is our compromise, the heuristic that we pursue in the NetScan algorithm for treating the articulation nodes. The runtime of the NetScan algorithm is order of I times k times capital E times diam over capital I, where I denotes the number of iterations which cannot be analyzed theoretically, diam the maximum pairwise distance, and capital I the chosen radius increment. So this algorithm promises to be efficient and scale well to large databases. Now let's move on to the last chapter, applications for joint cluster analysis. So this will be partly a report on experimental evaluation that we have performed already, partly we are sketching potential applications of the joint cluster analysis paradigm that we have started to investigate it over the last little while. So the driving motivation, yeah?
Can you explain again your example in previous slide, 2 slides before, where the constraints came in?
This one?
Yeah, so
the constraint is the internal connectivity constraint. Every cluster must be internally connected, meaning every pair of nodes in a cluster must have one path, connecting path, consisting exclusively of cluster nodes.
So it has to have a path between each node?
Yes, and the cluster center.
And where do you get the edges from? What do the edges represent?
Oh, the edges are input. We assume that the data is given as an informative graph, where we have both edges, basic nodes are associated with attribute information, and I mean, edges are assumed to be given from the data set. It's, I mean, we use the market segmentation as our driving application. In market segment, the edges would be social relations, for example, and the attribute data would represent demographic data, for example, in market segmentation.
So are you assuming that for like n nodes, you know all the relations for like all the n squared relations, connectivities?
For the case CKC problem, we are assuming that we know the graph structure.
How about I have some missing relationships?
That's a very good question. And it basically it motivates let me say less strict connectivity constraints. Right? In this original problem definition, we request that every cluster is connected. Right? So now, if there's indeed some missing edges, then basically we would not be able to find a solution to the CKC problem. Right? Now, we can one way of generalizing this is making the problem probabilistic, right? Allowing basically like smoothing the probabilities, right? Allowing to insert edges with a certain no probability, even if they have not yet been observed, right? But this is once more. I mean, this was the first step into this direction of joint cluster analysis. In the original problem definition, we assume complete knowledge of the graph of the relationship data as well as the attribute data.
So the radius is with respect to the distances between the attributes?
Yes. Radius with respect to the attribute data. So once more, in market segmentation, the radius would represent the similarity in demographics or purchase preferences between customers that are grouped together into one cluster. And the relationship would represent the social network.
The other question I have is articulation nodes. They seem to be the crucial constraint generators. So how do you, I'm not entirely clear about how you select them, because it seems like you could select many choices of articulation nodes would lead to different types of clustering.
Yeah. I mean, we determine them on the fly. As soon we iteratively increase the radius, right? We blow up the maximum radius that we consider in a certain iteration, right? As soon as we realize that the point is reachable, we perform this breadth-first search, right? In principle,
when you get to V, you take one step look ahead. You know that U and W can only be reached from V. And therefore, V is an articulation node, so you delay the decision.
We know that we perform breadth-first search starting from the K cluster centers, right? We increase the radius that we can go away from the cluster centers. So we know that V is reachable from both C1 and C2. We also know that it is within radius R from both of the cluster centers, right? As soon as we detect this, we look ahead, right? And we could look ahead. In principle, we could look ahead as much as we want to, right? Obviously, at the price of increased runtime, right? So what we do in our current algorithm is we just consider unary neighbors of these articulation nodes, consider their attribute values, their distance from the participating cluster centers, and use this as our input for the cluster assignment of this articulation node V.
For example, let's say the connection between V and U was a little shorter, was the same length as V and W.
Yes.
Right. So for the third circle, the third radius,
yes,
the U, V, W three nodes can belong to either C1 or C2.
If U was positioned, for example, here.
That's right.
Yeah.
So if U is positioned there,
yes,
for the largest circle, the largest radius, they would belong to both the cluster C1 and C2.
Yes.
And then you would have some kind of, you have to resolve the conflict at that point.
Yes. I mean, that's easy because in principle, we would like to grow the cluster simultaneously. We can't, right? In a sequential algorithm, we try the clusters one at a time, right? We perform a breadth first search up to radius Ri for cluster C1. If we can connect it to this cluster and have no articulation node, right, then we assign it, right? So basically, we consider the clusters in increasing number of the index. That's the way to resolve these ambiguities between different competing clusters within one iteration.
And so if there was an additional node Z, say, attached to either U or W,
yes.
so you only do one step look ahead, you essentially assign V, take the penalty.
Yes. And we are certainly aware of the fact that there's some room for improvement. Definitely. And we have investigated some alternatives, but as we have seen from theoretical analysis, this is an inherently hard problem, right? We can even, but I could complicate the situation a little bit further, but I want to refrain from doing this. Yeah?
So I have a question on
yes.
edge. So right now the edge only represents the relationship, right? Between
yes.
every two nodes.
Yes.
So I'm just thinking, is that a way to combine the relation and the distance, the attribute distance into one measure, and let the edge just represent that measure?
Yes. This can be done, and this has been done, and it's a feasible approach. But of course, you lose one thing: you lose the origin of this information, right? I mean, it's one of the strengths of this approach is that we can treat attribute and relationship data differently, right? Because we consider them as different data types, so we can treat them differently. It's
well, can we use a weighted average? Just combine them together, so we don't have to use the radius here.
No, we don't need to use the radius. As I told you, we are using the radius as the objective function only in order to analyze the theoretical properties of the algorithm and to design an approximation algorithm. Right? In practice, we would always use the k-means version of the problem. Okay, then let me move on to the application. We don't want to miss the application. Market segmentation had been our driving application, but as you all know, market data or customer data is very sensitive and hard to obtain. So instead, we performed some experiments using some DBLP data for community identification. And if you will, market segmentation can be understood as a special case of community identification. So we used a tiny data set with 50 orders described by the research interest attribute data and their co-order relationships. 2 class labels were manually determined for the orders. And this is also the reason why we use this tiny data set only, because we had to manually label the orders as belonging to one of the computing science research communities. This figure presents our experimental results comparing the K-center algorithm against the NetScan algorithm. And we observe that the NetScan algorithm can significantly improve the accuracy from 54 to 72%. All these accuracies, of course, relatively low, but don't forget that we are dealing with an unsupervised clustering problem rather than a supervised classification problem. Now, we also performed some more significant experiments using a larger data set, again based on the DBLP data set. So we extracted 1,555 papers with their term frequencies and co-ordered relationships. So we connected 2 papers if they share at least one order. We used conferences as surrogate class labels. So in this case, we could automatically label objects, documents, assuming that the conferences serve as surrogate for the communities. And our experimental results, again, are quite encouraging. And in this case, we were actually using the k-means version of NetScan as opposed to the case-center version. So we compared NetScan, the k-means version of NetScan, against the classical k-means algorithm, and we could improve the clustering accuracy quite dramatically from 62% to 77%. Now, why performs joint cluster analysis well on such a community identification task? Let's briefly take a look at this portion of our DBLP data set. The nodes represent papers, edges represent the co-authored relationships, locations of points represent the term frequency values. Now the line here in the middle separates the clusters discovered by k-means based on attribute values only. Now let's zoom into two interesting papers here. This paper by Fegin et al. On query strategies for price information. This based on the attribute values, on the keywords occurring in the title and in the abstract. This paper would be assigned to the database cluster, and this is what k-means ends up. Now, if you look at the relationship data, this paper is linked only to authors and papers from the theory community, and this allows NetScan to correctly assign this paper to the theory community. So the label NetScan labels it as a theory paper. There's also the opposite case when we look at this paper by Kempe et al. Gossip-based computation of aggregate information. This paper is more closely linked to, or more densely linked to database papers and database authors. It's linked to 4 database papers and only to 2 theory papers here. But taking into account the attribute information, the term frequencies, NetScan can correctly assign it to the theory community. Okay, so these were basically our originally driving applications: market segmentation, community identification, document clustering. Now let's consider some quite different applications for joint cluster analysis, such as gene clustering. Gene clustering is an extremely important task in molecular biology, with the goal of finding clusters of genes with similar function. Now, so far, only gene expression data have been used for this task, with very few exceptions. And there have been hundreds, if not thousands, of papers published on clustering gene expression data. However, it turns out that there is lots of relationship data available that could and should be included in the task of clustering gene data. Consider, for example, protein-protein interaction networks. Considering this kind of interaction networks would allow us to cluster genes that interact and have similar gene expression profiles. Considering the upstream sequence data that controls the expression of the downstream gene. Considering these upstream sequence data, we could cluster genes that share some transcription factor binding sites, and transcription factors are proteins that dock upstream of a gene and control the expression of a gene. So we could find genes that share some transcription factors and have similar gene expression profiles, similar attribute values. Last but not least, we could also make use of the wealth of published results of scientific papers. So we could, for example, cluster genes that are mentioned in the same article or in the same articles, which gives us some relationship data, and have similar expression profiles. And we have already some preliminary results on this application, which are very encouraging. Now, another application is clustering crime data for the sake of hotspot analysis. And criminologists, they are interested in finding clusters of crimes, which they call hotspots. In such an application, attributes would represent the numbers of crimes in a certain spot or in a certain small area within a certain period of time. Relationships would represent the reachability via certain networks, for example, the road or public transportation network. So how could joint cluster analysis be applied in such a context? Yeah, let's consider this toy example here, where we have a suburban, a downtown, and an industrial area separated by this river in the middle. Now, joint cluster analysis could find us these two connected areas of high crime spots. Note that this area here in downtown is connected via this bridge across the river. The surrounding areas would be partitioned into connected components of lower crime rates. So we would end up with one low code spot area, code spot here, another code spot here, another code spot here. These guys are not connected. And interestingly and importantly, this area of high crime spots would not be considered as a cluster because there's no connection between these guys. And this is what criminologists, for example, would want to accomplish in such a situation. So last but not least, I want to mention a somewhat more speculative application for image segmentation. So in image segmentation, we want to find clusters of pixels, the so-called segments, which hopefully correspond to some logical real-world objects. And pixels would be described by color values such as RGB values, as well as the relationships representing the neighborhoods, spatial proximities or neighborhoods of pixels. Now this slide actually shows some preliminary results of a student project from my class in the last fall term. On the left-hand side, we have the original images. In the middle, we have the NetScan results. On the right-hand side, we have the k-means results of a classical image segmentation algorithm. And it turns out that the CKC problem is quite appropriate to model the situation. The results of the NetScan algorithm are pretty competitive, if not significantly better, in particular in cases of very difficult to segment images. Okay, let me come to my conclusion. We have introduced the concept of joint cluster analysis, considering attribute data as well as relationship data. We have in particular introduced one possible problem definition in this paradigm, the connected case center problem. We have performed a complexity analysis. We have presented a 3 approximation algorithm. We have also proposed an efficient algorithm, the NetScan algorithm, that scales well to large data sets. We have performed some experimental evaluation that shows that the NetScan results are more accurate and, as we argue, more natural than the results of existing clustering algorithms. There are lots of applications such as community identification, market segmentation, gene clustering, crime hotspot analysis. These applications also propose some interesting direction for future work. I mean, there was already a question raised from the audience, what if not all edges are available? And this is, I guess, a practical concern in community identification, as well as, for example, in molecular biology. Normally, not all of the protein-protein interactions, for example, could be assumed to be known in advance. So there's certainly some future work that is suggested by some of these applications that we have discussed. I mean, there's actually different connectivity constraints seem to be meaningful in different applications. And here on this slide, I'm listing stricter connectivity constraints. there's both are cases that do make sense, in my opinion. There are certain applications where this connectivity constraint that a cluster needs to be simply connected is not strict enough. In certain applications, you want to find densely connected clusters, as specified, for example, by a certain minimum average degree, or as specified by a certain maximum graph diameter of a cluster. As we have seen already, I mean, there are also cases where a less strict connectivity constraint seems to be appropriate, accommodating missing data, unknown information in the graph structure. Another interesting direction is clustering without a priori knowledge of the number of clusters. I mean, this is a common criticism of the partitioning and clustering algorithm, that in many cases, actually, the user finds it very difficult to specify this number k of clusters in advance. And we are currently working on problem definition of joint cluster analysis that does not assume a priori knowledge of the number k of clusters. Here, the challenge is to balance the clustering accuracy, the radius, and the model complexity, right? We want to avoid the trivial solution of assigning each point to a singleton cluster. So we need to penalize complex models. The last topic that I want to mention here in my outlook on future work is overlapping clusters and noise. Like in the classical partitioning clustering algorithm paradigms, the CKC problem uniquely assigns every node to exactly one cluster. Now, there are both other cases. It's quite common that natural clusters may indeed overlap. In communities, for example, or in document collection, it makes a lot of sense to assign certain objects to multiple clusters. On the other hand, there may be points that cannot be assigned to any of the clusters in a meaningful way, which should be considered as noise objects. Now, so these are requirements that should be considered, which are, however, non-trivial. I mean, even for the classical case of k-means or k-center, for example, there are few very convincing solutions. The challenge here is that if we allow overlap and noise, we need to somehow restrict overlap and noise, again, in order to avoid trivial solutions. So we are currently working on some problem definition that defines an objective function that tries to define a balance between these two conflicting goals. So these are my references. Thank you very much for your attention. And I guess we have time for a handful of more questions.
Yeah, I just have one more question. Again, still on the edge. So edge is relationship, right? So right now, do you have any numerical value on the relationship?
No.
How strong
That would, no.
I think it's going to be very interesting if you have a numerical.
But you do have a way of measuring the violation of constraint, right? Or is that just a heuristic?
Yeah, I mean, no, I mean, so far, we don't need the heuristic for the violation of constraints. Our constraint in the CKC problem is very simple. That's a Boolean constraint. It's either connected or not connected, right? And this is strictly enforced.
But we can have numerical value, right?
We could. Yes, I mean, if we take this document clustering application, we could use, for example, the number of shared co-orders, for example, as a numerical weight, right? Or if we have, for example, in a community identification application, if we know, for example, how many emails these guys have exchanged over a certain period of time, we could use this to weight differently, right? But then we need to modify the connectivity constraint, right? Then certainly the current solution that just finds connected components would not be appropriate anymore, right? Then we need to have a certain, for example, we could use this version of where we have a certain graph diameter, right? So we could request that the cluster elements are reachable within a certain graph distance, so that the shortest path between a cluster center and any cluster member does not exceed a certain length.
Or you can use the connectivity times the average stress, right?
Yes.
On a related note, have you thought about how to reformulate the problem when you kind of alluded to it in your gene expression example, when you have multiple types of relationships. So for example, you want to use both the upstream binding
yes.
relationships and the protein-protein interaction relationship simultaneously.
Oh, I was not suggesting that. That could be an interesting thing. I was considering them as alternatives here. It's, but I mean, this is certainly now if we have multiple types of relationships.
Multiple tables.
Yeah. Okay, I mean, this is a question that we have not yet discussed. Yeah, I guess, I mean, that could make sense. But I guess this would be a major extension of the framework. I mean,
I can think of one trivial one, but I don't know whether it's useful,
yes?
right? Because you could keep track of multiple graphs in which all nodes participate.
Yes.
And insist on being connected in each of the graphs.
Yes.
But I don't know whether this is actually going to be useful because this is kind of conjunction, which is maybe too strong.
Yeah, or you could also require that nodes are connected in at least one of the graphs, right? This would be a simple extension. How meaningful it is?
Right.
If you just parameterize the edges, I mean, now edges would not be binary, but they instead of a single weight, they would have vectors of weights corresponding to connectivity in different graphs.
Yes.
In addition, if you can figure out the relationship between the graphs, you could think of it as a cascade of graphs. Like, remember in the Xbox thing,
Right.
exactly. You know, you are connected to somebody else and they play this game. So as a second order jump, you can pretty much get to this game. So something like that. If you have multiple relationships which can cascade into one another, that could also form some kind of a constraint.
Yes. We see. Yeah. I mean, as long as you reduce the multiple graphs somehow into one graph, right? Then we are back to this family of problem definitions. So, and I'm certainly not saying that this is not a meaningful direction. What I'm saying is, I would say, for the next little while, we would probably want to restrict ourselves to further investigate this problem of assuming a single attribute vector and a single graph structure underlying our graph. These, I think these extensions to take into account missing data, weighted edges, and so forth, I think are easier to attack than using multiple graphs, because we have some intuition of what we would expect from the problem definition and the solution.
Thank you.